make a small announcement. During the weekend, the caretaker will be away, enjoying his weekend. So there will be some security guards from a private company around. So they will go around, and sometimes at night. So normally they are not equipped with arms. But don't be afraid if you come across people looking around and with a uniform and so on. That's normal. Okay, so it's not the North Korea that has invaded. Okay, so let me introduce John Rehr from the University of Washington in Seattle in the US. So you might already know John because he's the lead developer of the FEF code. So, John, please.
Oh, okay. Well, first let me thank Didier and Jan and Hubert for organizing this in this wonderful place. And I must say, it's a pleasure to see all of you in 3.99 dimensions. The 0.01 is for the mask, but I think we can cope with that. So this is my talk, and what I want to talk about mostly is core level X-ray spectroscopy. So it's a little different than some of the other talks, but I think you'll see many overlaps. I'm going to talk, my talk will have four main areas. First, I'm going to talk about some sort of standard spectroscopies that the FEF code is designed to treat, namely XAS and XANES. They're described by this Feynman diagram, essentially. So this is what we have. This is a few 100,000 lines of code. I will only briefly talk about real space multiple scattering. Maybe you're tired of seeing these equations already, and you know them by heart. But I will talk about how the theory is used for a number of different spectroscopies. You've also heard some of that. So some of this will be repetitive. But then I want to talk about what kind of many body effects are important in understanding this core level spectra, in particular inelastic losses. And then finally, we've lately been interested in very high temperatures that are encountered with this next generation X-ray facilities like the XFELs, in which the electron temperatures are, the electrons are heated up to extremely high temperatures of the order of the Fermi temperature. Okay, so that's the outline. Let's begin by just looking at the phenomena. Of course, core level X-ray spectroscopy covers a very wide range. As you can see, it goes from the ultraviolet to the hard X-rays. And in a typical X-ray absorption, which covers about 10 orders of magnitude over this range, you see a lot of jumps in the spectra. And these jumps are edges. They're sort of atomic phenomena. But what's important is if you look closely next to an edge, you see a lot of fine structure. And this is what the experimentalists are interested in, because that contains a lot of chemical and structural information, solid state information. It's completely gone in atoms, or almost completely. So that's the task. And just to foreshadow, one of this is theory and one's an experiment. So it's not perfect because this is a log scale, but and this is a very old slide, but it'll give you an idea of the challenge. Okay, so now we look closely, and we immediately are faced with some problems. Namely, when we pull out our standard DFT code, in this case it was an LMTO code that my buddy Paul Balbers at Los Alamos had, he noticed that the code produced way too large wiggles at high energies. Of course, it was an LDA code, and it took us quite a long time to understand how to fix that. You'll notice there are two regions in this spectrum. This is the K shell of copper. So the edge is about 9,600 electron volts. And it rises very sharply. There's a little glitch here. And then in the first 10, 20 volts or so, the LDA code works fine. Hooray. But as one goes up in energies beyond that, you notice that the experiment shows a lot of damping features. And you can't, maybe you see it, but there are also shifts. So the structure is all messed up. And when they tried to extract structural information from this XAS, it was unsatisfactory. So what's the reason for that, and how do you fix it? It turns out this behavior reflects sort of very short mean-free path, as you would expect from that universal curve, a banana-shaped curve, at high energies. And there's also vibrational damping. What they say is that the fine structure melts if you heat it up. So you also need to consider vibrations, which a lot of DFT codes don't. They don't need to. So what we need is to develop an excited state theory. Well, a long time ago, my very first advisor, believe it or not, was Hans Bethe. When you get to the university, they assign you an advisor for the first year until you decide what to specialize in. And since I didn't go into nuclear physics, I couldn't keep him. But this guy was amazing. He always remembered you. And about 10 or so years later, he came to University of Washington, and he says, "Well, John," in his German accent, "what are you working on these days?" And I said, "Well, I'm trying to calculate X-ray absorption." And this is what he said. So that was and he laughed, actually, because he appreciated the challenge. Okay, so I call this the Bethe challenge. And I was a young guy. I didn't know better, so I persevered. Okay, so our approach that seemed like a good idea was actually started by Patrick Lee, was to use a real space multiple scattering theory that you know all about. The theory is described really nicely in this book by Didier, Keisuke, and Hubert. And our patented approach based on this is the FEF code, which is described in this Review of Modern Physics 2000, also done with Bob Albers. And I'm proud we got the cover for this. Okay, so as you've already guessed, this is a no wave function shop like we found in this school. It's way better to calculate X-ray spectra not using the golden rule, but to use Green's functions. And the problem with the golden rule is that this is a sum over states method. And for very broad energies, it's a waste of time. Basically, you have to first solve the Schrodinger equation for all of these final states, and then you have to sum them all up, and then what my buddy Bob Albers said, and then you have to broaden the whole thing out. So you start with milli-Rydberg accuracy, and you end up broadening out all the structure. So the Green's function is obviously better because this expression can be turned into a single matrix element of the Green's function between a dipole excited initial state, which is a core level. Okay, the non-standard thing about our approach, though, is we have to consider damping. And so our Hamiltonian, I call H prime, is not the ground state Hamiltonian at all. It's the excited state Hamiltonian. which is the ground state Hamiltonian plus the potential for a localized core hole of the edge that you're interested in, and then a dynamic and complex valued, what I call self-energy. And it's the self-energy that contains the mean free path. But it also contains a real part. So this is the tricky part to get in. And you see, I've crossed out VXC. Maybe you'll be happy about that because nobody knows what it is. And well, it's hard to calculate this too, but it's a difference. It changes the problem. Okay. Here we go. So just to summarize, in this school, there's been a lot of discussion about what a Green's function is. It's different. It's very similar to the wave function in many ways. I mean, it's a sort of a similar Hamiltonian, except in this case, it's a driven or inhomogeneous Schrodinger equation. At least the one particle form is. And this Green's function is sometimes called the propagator. So this is the amplitude, quantum mechanical amplitude for a particle that starts at one point, r prime, and goes to r. And all the many-body effects in this one particle equation are in the self-energy. What we've used to calculate the self-energy is usually this famous GW approximation that Lars Hedin wrote down back in the 60s. And it's usually obtained from many-body perturbation theory, in this case, first order in the screened Coulomb interaction. So I'll touch on that very briefly as I go on. And if you want more details, maybe you know this book. Fabulous book by Martin Reining and Separable. Lucia Reining actually plays a major role in some of our recent developments. She's a theorist at École Polytechnique in Paris. Anyway, right, I recommend the book. It's very modern and up to date on many-body theory and a pleasure to read. Okay, what's the self-energy continued? All right, so the GW diagram I write like this. G is the Green's function, of course, so that's a green line with an electron going forward. And this dashed line is the coupling to plasmons in the case of electronic structure. And if you look at the mean free path, for example, that comes from the imaginary part of the self-energy. And here I've plotted it. So I plotted the real and the imaginary part versus energy just over the first couple hundred eV. And so it's interesting. What you see is that in the low energy range, below the first excitation energy, or the dominant excitation energy, which is the plasma energy, which is 10 to 20 volts, more or less it's universal. This is why the curve that you saw for the mean free path is universal. The self-energy is sort of has a weak imaginary part and very little variation in energy, so you can get away with DFT codes. This is the range where they work great. So first 20 eV, no problems. The problem is that if you really want to do Zanes, like what Ben Fado was treating, going out to 200 volts, you're in trouble. And this slowly turns on. It goes to what's called the inner potential in materials, which is complex. And it's several eV, and it's damped. So at high energies, you can think of an electron as moving in a lossy medium. Okay? And so if you use as your energy reference a muffin tin 0, which is lossy, and use that as a starting point, you have damped Green's functions, G zeros. which is sort of like the screen KKR, just tuned for this problem. Okay, anyway, keep that in mind. That's what has to go in there. And so what the SelfEnergy does is it basically shifts like an accordion the spectrum and damps it. And let's see how it works. So to summarize, it's like lossy DFT at low energies. See this imaginary part? It's 1 or 2 volts. It's like that banana curve, not 0. And you can get away with just Lorentzian broadening if you want. Okay, so just very briefly, I'm going to go through a bunch of slides. You've really seen this before. So it's a recap. How do we get to this equation? Well, we start with the many-body Fermi golden rule. And these are then initial and final n-body states, n being 10 to the 23rd. Okay, so we don't want to do this. So we represent these in Slater determinants, and this immediately goes to a one-particle Fermi golden rule and an overlap integral, which sweeps all the other states under the rug into a constant factor, which people have called S0 squared. It's the overlap between the states with and without the core hole. Okay? It's not a perfect overlap. This is typically about 0.9. Okay, so then we have the sum over states problem that I mentioned that you don't want to get into. And so if you do sum over states, and you do this by replacing this with the Green's function, and this is implicitly the spectral representation of the density matrix, then you get this equation that you've seen before, that I wrote down. However, the theta function is actually a broadened step function, broadened by the core hole. And at finite temperatures, this would turn into a broadened Fermi function. Okay. Of course, like the KKR, we use a local site and angular momentum basis everywhere. I is the site, and L is the angular momentum. And of course, I've used capital L, but really it's a relativistic angular momentum basis that you really need. And so if you put that in, this calculation of the X-ray absorption becomes a product of matrix elements, local matrix elements between a core hole, a dipole operator, and a state IL. We have to sum over L and L prime. So what we need is this Green's function matrix. And you can guess how we get it. Basically, we use the site scattering T matrix and get this equation. And we invert, finally, to get the Green's function, 1 minus G0t to the minus 1 times G0. So it's very similar to the path operator. But we go for the Green's function, just to avoid just calculating the path operator. It's equivalent, completely equivalent, believe me. So we sum this to all, this can be summed to all orders by inverting this big matrix. We call that big G in our code. Okay, so but I like to think about the physics. So when you're faced with inverting a matrix, you got to look at the dimension of the matrix. This is a site angular momentum basis. So the dimension is n, number of atoms in the material. And for these problems, you can get away with a cluster. We do it in real space. And this is L times L plus 1. I just call it L squared, L max. What's L max in materials? Well, in the near edge region, L is sort of up to F electrons, so it's 3 or 4. So it's like 16N. Not too bad. But how about XAS. L is 25. And so now we have 625 times maybe a few hundred. How do you like inverting those? You quickly run into computational difficulties. And so this is only practical to do this matrix inverse at relatively low energies, no matter what size computer you have. I don't think you can really get it much higher than a few hundred eV when you're lucky. And if you need to invert, have a lot of atoms in your problem, like you're doing a surface or something cool with some impurities, anyway, you see how it grows. So you have to pay attention to the matrix to see what's possible or not. Of course, at high energies, what we have going for us is this very short mean free path. Okay? And so then, theoretically, you'd think the equations would converge faster, right? But they don't. Why? Because the dimension is Ln times L max squared. As I said, it's huge. You can't sum this thing using Green's functions. Well, you can, maybe. I mean, but it becomes numerically demanding, shall we say. Okay, so what to do? So this took a little while, but if you stare at the Green's function at very high energies, you realize that physically it should reduce to the plane wave approximation. And in that limit, the Green's function is separable. It's e to the ik r over r times the product of spherical harmonics. So I stared at that, and believe me, I stared for a very long time, and realized that if we could make a separable representation of the Green's function, then maybe we could make this faster. So what you have to imagine is rewriting this, taking every Green's function line and cutting it in half. Okay? These are our separable parts. And we'll call the separable parts these F matrices. This is sometimes called a cut diagram expansion. It's like taking a diagrammatic expansion and cutting the lines in half. This is used a lot in theoretical physics, and it's very clever. It's basically a separable representation of your operators. And whenever you can get away with it, it is great. And it turns out, as DDA said, thank you DDA for testing this, it turns out that this converges very rapidly. Oops, sorry. And you can get away with 6 by 6 matrices. At high energies, in fact, it goes down to 1 by 1, but it doesn't matter. It's so fast that you may as well use 6 by 6. In photoelectron diffraction, Fadley and his group went up to 10 by 10 in some cases, but usually you get away with it. So, okay, I've summarized this here. This is our separable matrix. And the cool thing about this separable matrix is that now you can sum all the L's at one site all the way up. Okay, just like in the expansion for the scattering amplitude in potential scattering. You remember the equation, sum t to the L PL cosine theta or something like that. Okay, you sum over all L's. We go up to L equals 25. That's about 1,000 volts or 1,500 volts. So the conversion is that L max is sort of the same as K max, and K max squared. K is done in Rydbergs, so at 1,300, then K is about 10. 10 squared Rydbergs 1,000. Okay, anyway, so this is what we have. And now we can do this path expansion, path by path. And for each path, then, we have, let me go back a little bit. a different product of these paths. Okay, and you can think about this then as the sum of all possible ways that an electron can go through the pinball machine and end up back at a starting point.
Sorry.
Oh, yes.
How do you introduce the separability?
How do we do which?
Yeah, introduce a local basis set and project on that, or
Say again, sorry?
do you introduce some local basis set and project on that to have a separable matrix?
No, it's all done in angular momentum. It's just taking your structure factor, your G, and writing it as two F's like this. Oh, it's a very, actually, I recommend you take a look at the Rehr paper. It's like a double spherical harmonic expansion. It's sort of the same angular momentum algebra. It's very pretty, but it's a little technical. I prefer not to go into it at this time. It would take, it's an algebraic game. What would you say, Didier?
Yeah, I would say that the only simple part in your approach is that it involves the rotation along the z-axis, and you compute the propagator along the z-axis.
Yeah.
The matrix elements of the propagator along the z-axis.
Yeah, you need Euler angles to rotate it and back. Anyway, it's a wonderful bit of angular momentum algebra. I like it. Okay, in the end, the upshot is that for each path, then, you get a contribution to the scattering that has the path distance. So you sum them all up. It has a denominator, 1 over r factor, because we're 3 dimensions. It has, you can put Debye-Walder factors into this just by the fluctuations in the path length. And then you get a trace over this. It's just a trace over products of 6 by 6 matrices. So it's lickety-split. And you can do thousands of paths in minutes. So the beautiful thing, though, is you get a form which looks like the original plane wave expansion for the scattering that has all the terms that you want. Okay. Well, there's another way of doing it. In fact, like Feynman, I've learned to try to do calculations several different ways if the standard way doesn't work. And I don't know if other people have used Lanchos to do KKR inversions. Do you know? Anybody? Lanchos is a wonderful way of doing matrix inverses. It's basically an iterative approach that interpolates between sort of full matrix inversion and then a fast matrix inversion where there's just like a single pole. Anyway, it's used by the quantum chemists a lot. So when you're trying to do something like silicon, which has a very long mean free path, you need lots of atoms, about 500 or 1,000. And this technique converged slowly. But it turns out if you use Lanchos, for the first 20, 30 volts, it starts at about 1830. You need full multiple scattering. But then it turns out that slowly, as you go up in energy, the number of iterations, Lanchos iterations you need is very small. So it converges to the path expansion and sort of makes a nice way of combining the two. Okay, something else nice, and this is probably used in KKR too. What you notice is that this expression for Fermi's golden rule for a given edge just has energy as a parameter. There are no eigenfunctions in this whole game, except for maybe the atomic core levels, but they're discrete. You can solve them. Okay, energy is just a parameter. So the whole game parallelizes naturally, and you can give a different energy to each processor in your cluster and calculate the whole spectrum, press of a button. So this is really quite nice these days. coffee break time for calculating spectra over wide ranges of energy. And this is how they do the experiments. They don't do every energy, obviously. They pick a range over which the spectra is pretty smooth, you know, maybe a half volt resolution or a tenth of a volt, whatever you want. Okay, so we put all this stuff into the FEF code. This is the matrix element, and this is just part of the FEF code. This is the single particle contribution to X-ray spectroscopy. Okay, you want to do deep core levels, and you want to do them for everything in the periodic table. So it makes sense to start with relativistic Dirac-Fock solver. We use a solver that was done by Desclos. We got it in Fortran 4 from him and sort of upgraded it. So this builds in spin orbits and all that stuff. It's all electron, which you need for magnetic problems, as you know now. It's essential to make it self-consistent. We use these overlapped muffin tin potentials. Default overlap 1.15 or 2, something like that, 1.2. That seems to work pretty well. We are very envious of the full potential KKR people. We've tried to implement that, but we've never managed to finish it. Okay, Green's function propagators done with the real space Green's function theory, just like KKR, except that ours are built in the inelastic losses with the self-energy. The core hole is really an essential thing. I'll talk about how to get that, but typically it's a screened core hole. It's one of these miracles of condensed matter physics that the core hole localizes. And it's not a block wave. The X-ray finds the electron, always seems to be from one of those core levels. So prove that. That's a challenge, but it's true. Okay, anyway, we have the self-energy. And what I said was we need Debye-Waller factors. And I put this last, but it always comes back to haunt you. Without this, you have a 90% theory, if you like, or 80% theory. If you're satisfied with 80% theories, then you can make this a constant, 0.8. And that's a default. Who was here that says, oh, maybe he left. He says every good theorist knows how to make the first approximation is a constant. So that's our excuse. Okay, so let's look at XAS theory, see what we have for the beta challenge. I've written down this famous equation. I don't know if you all know it, but it's written down in the 70s. I can't count how far back that is. But this is the equation for those oscillatory parts of the fine structure. They're sinusoidal, and they contain the path length. 2kr is like the distance that an electron travels to a near neighbor or back. Sorry, it's the phase that you get when an electron goes to the near neighbor and back. It's damped by the mean free path. These are the Debye-Waller factors. And this is a scattering amplitude for that particular path. And there's a spherical wave factor. It's r squared because it goes forward and back for single scattering. So that's twice. So fortunately, you get an r squared. So you only are sensitive to a few near neighbor contributions. That's really great. So you don't have to do a lot of work to get this. But if you look at the parameters, what do we got? Okay, what we have is that energies, you have to go out to 1,000 volts in the continuum. That means you have to go up to angular momentum L equals 25. I don't know if you've ever played with angular momentum up to L equals 25. Helps Gordon coefficients. You know, you have to calculate L factorial times L plus 2 factorial over M factorial. Try that with 25 factorial on your computer. I guarantee you it will give not a number. Maybe you can do it with quadruple precision. So yeah, you have to do fancy angular momentum algebra. It's just tricky arithmetically. You have to calculate all these scattering amplitudes and phases, put in the mean free path, energy dependent, of course, put in a core hole lifetime. I didn't discuss this, but it turns out that there's an intrinsic lifetime for every core level. This is because of Auger recombination. The core hole doesn't last forever. And this gives an additional broadening because of the delta E delta T equals H bar uncertainty principle. Okay, vibrational damping, every path has to be damped. And finally, we put in a fudge factor for the S0 squared. All right, push the button. Okay, now this is an old slide. You see it's 91. So that's 10 years after Hans Bethe. So he was right. But here's theory versus experiment for these phases. I think I have platinum, copper, and some molecule. One of my early grad students had this problem. It's Jose Mustre de Leon, very smart grad student. But it was one of these thesis projects. The first thing he did was he put in the Hedin-Lundquist GW SelfEnergy. So that was, he thought, now I'll get my degree, you know, because he worked so hard to get that in. And the answers got worse. And finally, when he got these separable approximation in, the curves went just the opposite way and canceled that error out. And the result was that the curves were on top of each other. So we were really happy with that. The other nice thing is that you know, people always criticize some of us for using spherical muffin tin potentials. But it turns out at high energies, the centrifugal barrier, maybe DDA pointed this out, is very deep inside the atom. Okay? And inside an atom, even if it's condensed matter, potential is really spherical. So what happens is that after about 20 or 30 EV, the spherical muffin tin works great. And so that's a redeeming feature of doing XAS. So you know, you win some, you lose some. The angular momentum stuff was tough, but at least we didn't have to fuss too much with the full potential, except you have to get the edge right. So you need self-consistently. Okay, another thing they do in XAS is they take a Fourier transform of that oscillatory structure. And as you can guess, since it goes like the sine of 2kr, the Fourier transform has to have peaks. And it has peaks at the interatomic distances. So that's why this technique is used as like an X-ray microscope. And so this was platinum. I think it was done by us using data from Matt Neuville. And one of these is theory, one's experiment. I can't remember which. I guess the red's experiment, the green's theory. And no adjustable, we had one adjustable parameter, the S0 squared. But I think you can see it's really on top of each other. And that's remarkable in physics. You know, rarely do you get curves that are so tight. And you can see that the peaks match the structure, the radial distribution function of platinum, FCC material, pretty well. In fact, the accuracy is about 1/100th of an angstrom or better in this. It's not quite like XRD, but it's close. So this is my answer to Hans. It's a partial energy answer. So if you know the structure, then this theory does a good job of calculating the fine structure. But so it doesn't tell you what the structure is, but at least says that this is a good way to fit to get structural information out of an experiment. Okay, what's also nice about this is that you can get a physical interpretation of the wiggles because of the dipole selection rules that have been mentioned, at least for the K-shell, when you're going from S to P. What's measured in the X-ray absorption is like a broadened P density of states. L equals 1, final states. And you can see one's the XAS, the other's the electronic structure. So this same code that we have, if you don't broaden it, gives you the P density of states. And similarly for the occupied part, which is like X-ray emission. So that's nice. And similarly, if you go from L shell, you get mostly L plus 1 final states. Okay, so that's the story of XAS and Zanes. We have an algorithm for calculating all those things. What about some of these other spectra? So RIXS, non-resonant inelastic X-ray scattering, is essentially like X-ray absorption, except the transition operator, instead of being a dipole operator, is just an exponential, e to the I q dot r. So what you're measuring is the dynamic structure factor. And we can do the same trick. Instead of having a dipole operator, we just put these exponentials in there, but we use the same code, same path expansion, same everything, and all we get is, in this game, is now a momentum transfer dependence in everything, and it's summed over the local density of states for every L. And we check this against very high level codes, beta saltpeter codes, and an experiment. As you can see, they're in pretty good agreement. So the codes work quite well for this RIXS. RIXS is nice because you can do it on low Z atoms like water very easily. Okay, how about EELS? The cool thing about EELS is that it's also similar to X-ray spectra, but nowadays they're getting better and better machines, which means the beam energy is higher and higher. Now 300,000 EV, and guess what? It's no longer a non-relativistic calculation. What happens is that the Q vector gets Lorentz contracted along one direction. And this messed up the magic angle that they found in polarized EELS calculations. But otherwise, it's similar. It's easy to correct this. And we can do EELS quite accurately. And you can put in collection angles and that other stuff as well. Another aspect of EELS, or actually KK, or any kind of core spectra, is that the main difference between ground state calculation and calculations with a core hole is that there's an additional T matrix at the core. And it's just one of these T's that's different, ignoring a little bit of overlap with next shells. So if you can put in this core hole instead of using a supercell. I don't know what you guys use for, do you use supercells to treat core XAS, or do you do this kind of game? Well, anyway, this is nice, and it works. You get the same results without using supercell. Okay, well, it turns out you can do Compton too. You have the Green's function, so you just do a Fourier transform, and you get the momentum density. And we compared it with a KKR code. I can't remember whose it was. These are shifted from each other. But you can see that we really overlap the experiment just as well as the KKR. Compton is also used as a thermometer. in these warm dense matter experiments because it measures the momentum distribution. In fact, I think Compton was one of the first experiments used to prove the fermion nature of electrons. So they have this cutoff there. Okay, and most recently, we've been doing high throughput calculations. This is in collaboration with the Materials Project. They wanted to have a database that had all the X-ray calculations for all of their materials, and that's available now. You can go into their database and click on any material you want, and you'll see the near-edge spectrum calculated. And they've recently been adding L, but they also provide a SIF structure file, which they get from VASP, and a FEF input file. So this is a good source of input files for doing a lot of condensed matter materials. This is not molecules, but it's there. And this is very recent. It's not published yet, but we've extended it to calculate all optical constants. Now, I don't know if I can click on any of this without messing up the code, messing up the thing. Can I do it? Maybe not. So can you click on that periodic table of optical constants?
So you have to come out.
No. Okay, sorry.
We have to come out.
Oh, no, too much. All right. Well, anyway, you'll get the slides. So I encourage you, when you see the slides, click on that periodic table of optical constants. We've done all the elements in blue, and if you click on it, you will get a list of optical constants like absorption and energy loss, but you get it over the whole spectrum. And you see we go from, what is this, 0.1 EV to 100,000. So basically we've stitched together the edge, all the edges, and done in high throughput form. Okay, there's also a lot of interest these days in RIXS. RIXS is a nice spectrum spectroscopy for getting excitations. It's an input-output, photon in, photon out spectroscopy. The theory is a little bit daunting because you have to solve this so-called Kramers-Heisenberg equation. Sum over states, right? Don't go there. Anyway, so you get pages of algebra. What we've done is to ignore the interference terms at our own peril. But when you do that, it turns into this beautiful expression, which is essentially the convolution between the emission spectrum, an absorption spectrum, and a resonant denominator. And you calculate these just with FEF independently, and one's theory, one's experiment. So since RIXS is mostly a fingerprinting-like game, looking at the peaks to get the excitation energies, it seems to be reasonable. Not always, but you know. Anyway, this is an approximation. It's not completely accurate, but it works pretty well. Okay, finally, how am I doing on time?
Just if I may interrupt, did you try to compare, to assess the level of the approximation? Did you try to compare to a RIXS code? I think they do it maybe with multiplets or what else?
Yeah, we're doing that now, but actually, I had a postdoc working on this, Soinen, and it was a nightmare till we found this approximation. So I would say our work was incomplete. And we gave up on Kramers-Heisenberg. We turned that into a Green's function calculation too, but okay. Well, I leave it as a challenge to you to get it with KKR. Maybe there's a KKR RIXS. Okay, so let me, how much time do I have?
You still have over half an hour.
Okay, good. Okay, so this last part is actually fairly long. When we first started, we had various approximations for some of the many-body effects, like the Debye model for those Debye-Waller factors, and Hedin-Lundquist plasmon pole approximation, which gives a pretty good banana. It's universal, but it may not be as good as you can. And then we had that nasty S0 squared term. So we decided to see if we could improve the calculations. Now we're up to 2009. This is a nice review article. It was actually edited, maybe you can't see, by Lucia Reining. And it has sort of the state of many-body theory and codes at that level. So I recommend that. And this is sort of the state of the FEF code at that vintage. Okay, so first of all, the core hole. We used to use DFT screened core holes. You just put a core hole in, bare core hole, and let the electrons do what they want with DFT screening. And that gives you this so-called final state rule screening. On the other hand, if you just do linear response, RPA screening, you get a curve that is very similar to that, but it's probably better. Anyway, the RPA is what they use in the beta-salpeter equation. So to get a correspondence with beta-salpeter, we can also use RPA. They're both about the same, as you can see. And what's interesting is that they both come to about half a full core hole. That's another popular approximation. They take a half core hole, and they call that a Slater transition state core hole. Well, anyway, that's the core hole. The RPA is nice. It's fast and agrees with beta-salpeter. So that at least is consistent with many-body perturbation theory. The final state rule is an ad hoc thing that is sort of these magical rules that work better than they have any right to. How about the self-energy? Well, I said we use GW. The W is a screened Coulomb potential, which means you need to know epsilon minus 1 times the bare core potential. This is what epsilon minus 1 looked like. This is called the loss function. It has peaks at the excitation energies, namely the plasmons in a system. And in metals, you get a really nice sharp plasmon peak. In anything else, you get a bunch of peaks that peak around here. And what's interesting is that this explains why the banana is so universal. There's always kind of a big peak at 20 to 30 EV. It's remarkable, even in insulators. So there's something to this plasmon pole approximation that's very universal. Okay, but this is what we use to improve things, but it requires a calculation of the loss function. Anyway, we put that in, and we get ab initio self-energy effects, real and imaginary parts. This is 2007 now we're up to. We've improved our atomic code. There's now an interest in superheavies. They've discovered a few of them, 119 or whatever. This is seaborgium, which is 106, and they actually have experiments. So we took our code up to 138. So it's sort of nice. And what else did I want to say about this? Oh, yeah. This is very interesting. What they said, there's a theorem that the Dirac equation fails to converge above 1 over alpha above 137. You know this theorem. If you look at the Dirac equation, you see there's a square root of 1 plus something like z over v, or something like that, zr over v. Anyway, it didn't blow up. We thought our code would be dead. And the reason is that when you get up to that high energies, the s orbital actually starts to penetrate the nucleus. So you never see the full point charge. You see less than that. And actually, so you start seeing nuclear effects. Okay, ab initio Debye-Waller factors. Debye-Waller factors are formally calculated by these Debye integrals. This is n plus a half h bar omega, and this is the density of vibrational states. We use one of these Lanchos approaches. Take the spectrum and do a Lanchos approximation with it. You only need a few poles because you're doing an integral. And it doesn't make sense to calculate the whole spectrum and then integrate over it. So this works quite fast. Okay, so let's see what it does. We worked with our French collaborator, Xray. I guess she's not mentioned here. And they have the Paratech code doing Xray spectroscopies. And this is FEF with all these many body effects in here. And so here's what you see. The Paratech gives really nice treatment of all these peaks, but they get systematically shifted. Experiment is the red, and damped. But when you put in the SelfEnergy, it basically tracks the shifts and the damping, and seems to correct the details pretty nicely. Okay, of course, close to the edge, everything is just fine. Okay, what's missing? This is our friend, the many-body overlap integral. What the experimentalists noticed was that the theory always overestimated the fine structure. They always gave us a lot of trouble, you know. So, of course, all they did was took the theory and multiply it by a fudge factor, which is just fine. I mean, all the peaks are cut down by about this fudge factor. But that's not satisfactory to us. And I said the reason for this is called intrinsic losses. They're the losses that are created when you turn on the core hole suddenly and you create a whole bunch of excitations. So now the photoelectron has a renormalization constant z in front of it. And there's this extra factor. Okay. It turns out that what we do is now we have to, instead of the core state being a delta function, we need a core spectral function that includes this response to the suddenly turned on core hole. And essentially what this does is it leads to a convolution of the core spectral function, which you call A. It's just the imaginary part of the core hole Green's function, and your one particle Green's function, like so. Okay? How do we calculate it? There's a standard method for calculating self-energies called the Dyson equation. And of course, naturally, we don't want to use the standard approach here. It turns out there's a problem with the Dyson equation. Dyson equation works beautifully for the quasi-particle, but it works terribly for calculating effects beyond the quasi-particle. What Lars Hedin said was if you want to judge the quality of a many-body problem, always look at how it treats the satellites. That's what Maria this morning said were those peaks beyond the quasi-particle. We use something called the cumulant Green's function, and in the time domain, this is just a product. So this is the full Green's function for the core. This is the bare core hole Green's function, just a delta function, e to the I omega t, Fourier transform. And the cumulant has all the many-body effects. The beauty of this is that it builds in the vertex function. And it does a good job coupling two excitations. I really recommend it. There's a nice review by Sky Zhao, who's a student of Lucia Reining, in this issue of JChem Phys. But it's quite beautiful. Also in Lars Sedin's 1999 review. Maybe I have a reference for it. Okay, so what's going on here? Well, if you look at some correlated material, like a transition metal oxide, this is copper oxide. It's not too correlated, but it's a little bit correlated. What you notice is that the single particle theory, where is that? Here, like Pfeff, seems to miss some of these peaks. And this first peak, this edge, is too big. What the French did, this is Calandre and Christian Brodeur and company did, was they said, okay, well, we know the excitations are in the XPS. That's what the XPS has. So we'll just do a convolution of the single particle theory with the XPS. And this is what they got. And I think that's really nice. So we tried to duplicate that. And with our cumulant, we tried it out on, this is titania. This is a 2p, 3 halves and 1 half. And as you see, you get these main peaks from the quasi-particle and then the satellites. But the cumulant sort of nails the satellites. Maybe this is a little too big. But it's really accounts for now the whole spectral function, including the width, this quasi-particle broadening. It also explains the nature of the plasmons in these materials. These are correlated materials that have a charge transfer excitation. And the charge transfer excitation seems to come from charge transfer from the p ligands, these are the oxygens surrounding the titanium, to the d orbitals unfilled in the titanium. And this is a Fourier transform of what the charge transfer excitations are due to this suddenly turned on core hole. So the picture of these satellites is you turn on a core hole, and what are the electrons going to do? Well, the near neighbor electrons on the oxygens notice there's a core hole there. So they start moving toward the core hole, but they can't stop there. I mean, it doesn't get trapped. It actually is a kind of oscillatory state. It's a transient state which has a long lifetime, and that's why you get an excitation and some loss. You're creating a sort of a long-term excitation. Okay, and if you look closely at the theory, you'll notice that we cheated a little bit when we calculated the intrinsic part and the extrinsic part, because in quantum mechanics, you're supposed to add amplitudes. And so we missed a couple diagrams. These are called interference terms that are sort of the interference between extrinsic and intrinsic. And if you add these all up, you get a kind of perfect square of diagrams that Schrieffer solved using the cut diagram approach. That's the first place I learned about it. So we have a slightly different approach, but the upshot is you can put all of these into a single particle hole spectral function, which is then convolved with a beta saltpeter-like particle hole, particle hole spectrum. It's not one particle, it's two particle, and then get all of these, take all of these into account. Okay, well, does it work? We tried it out on nickel oxide. It actually does a pretty good job. This is the experiment, the dots. And if you just have extrinsic and interference alone, you get not quite right stuff. But put in the interference terms, it fixes it all up. So now our cumulant has an extrinsic, an intrinsic, and an interference term. But it's sort of similar arithmetic. Okay, now how about F electron material? The F electrons are really strongly correlated. In fact, you often need multiplets, but in this case we didn't. You can see how big the satellite is compared to the quasi-particle. It's 30 or 40%. And they're huge corrections. Okay, it doesn't work quite as well here, but the particle hole cumulant gets closer to the experiment. The single particle F calculation is way too big here, but it sort of fixed it out. So the result is that you have very strong satellites at low energies, and this cumulant Green's function approach seems to improve it, even in fairly correlated systems. So it's really remarkable, this cumulant. It's like getting a vertex into the formalism. Okay, and finally, let me go to high temperature extensions. We were led to this because there's a new theory center at SLAC. It's called TIMES, the Theory Institute for Materials and Energy Spectroscopies. And it's designed to treat spectra coming from XAS, things like the LCLS, pump probe experiments, etc., where you need to include temperatures much bigger than the Debye temperatures, sort of 10 to the 4th, 10 to the 5th Kelvin. This required quite a number of extensions to the code. Now I know you guys have finite temperature in the codes. I'm not sure you treat the lattice temperature and the electron temperature separately, but you have to do this to treat XFELs, because what happens is when you suddenly heat up the electrons, the lattice doesn't have a chance to move. So the lattice is stuck at 300 Kelvin. The electrons are then up there at 10,000. And you have a non-equilibrium problem to deal with. Everything else changes. You need finite temperature self-energies, exchange correlation, and Fermi factors. This is published now, by the way. Oh no, this is not 2017. I have the wrong. This is 2021. It's just out. Okay, what are the ingredients? Okay, the chemical potential goes way down, but it turns out it's really quite amazing. You can get away with this Sommerfeld expansion, which is a simple parabola, up to weigh 10 electron volts, 10 to the 5th Kelvin. It works pretty good. But basically, the continuum is lowered. That's what they say. The Fermi level goes way the hell down. And so you can see states that were formerly occupied. And so that's sort of interesting. This is the exchange correlation potential. And this is our calculation. It's done with a finite temperature cumulant expansion. Nice thing about it is that low temperatures, when you're only at 0.1 times the Fermi energy, which is 1,000 volts or so, it's pretty flat. So DFT works just fine up to 1,000 Kelvin. It's the excitations, things like spin and or vibrations that are really temperature dependent. Okay, but the DFT is fine up to here. But when you get beyond this, look at this. The exchange correlation sort of turns off. And what turns off is actually the exchange. Things become more classical at high temperatures, as you would expect intuitively, right? So, yeah, electrons are no longer tightly correlated. And we agree quite well with this so-called KSDT fit to quantum Monte Carlo. So it's we have a very good finite temperature exchange correlation potential. This is also interesting. If you look at the real and imaginary parts of the quasi-particle, it's shifted by the self-energy. And the real part of the self-energy actually gets much smaller. Well, it gets cut down by a factor of 2 as you go up in temperature. So that's nice. But look at this. The imaginary part grows. And that means that you're sort of like in a dense plasma. You're really nearsighted. Everything is metallic. It's kind of interesting. And all the band gaps are smeared. The band structure is blurred. Forget the band structure. Everything is get away with sort of damped free electrons. Very nice. Okay. Electron versus lattice temperature effects. Okay, what I said, the electron temperature is very high. So you start seeing formally occupied states, and you get a sort of damping above the Fermi level, because you basically have to think of a Fermi function now. You've cut down on the number of unoccupied states, and you've raised the occupied ones. The lattice temperature acts like a Debye-Waller factor. It gives more damping as you go up. And you need both of those in there. This slide is just to show the separate effects. In fact, what you need to do is a kind of two-temperature model. And as you go up in time, say up to 20 or 30 picoseconds, it takes that long for the system to equilibrate. And it does so by transferring energy between the electrons and the lattice. This green curve was work done by David Prendergast and his students. And the blue curve is the finite temperature FEF, and then their experiments. So it seems to be in fairly good agreement with the time-resolved near-edge calculations. Okay, well, I'm almost out of time. I did want to mention these next-generation software initiatives, Times at Slack. We also have a new version of the FEF code, which I invite you all to download if you want. And this has an open source license, so it's you have to register, but there's no fee. And there's also an initiative at PNNL. This is more quantum chemistry driven, but it's couple cluster, etc., real time, but more quantum chemistry related. So here's some conclusions. We've pushed this real space Green's function theory quite a while now. It's well developed, I'd say fairly accurate. We wanted a pretty good theory. We didn't want a perfect theory. I mean, we wanted to go as far as reasonable in reasonable compute time. You can, of course, make it more complicated if you want. It's broadly applicable. So I think you'll find that the code's pretty easy to use. This is the main conclusion. The self-energy and vibrations are really essential for quantitative core level spectra. Maybe in the Zanes you can get away with without it for the first few EV, but it's really essential. And this cumulant spectral function actually is really nice for putting in effects beyond the independent particle approximation. It gives you this S0 squared. It also gives you satellites, which are usually smeared out in the experiment. Okay, well, this is the FEF10 code for, that we have for a whole bunch of spectroscopies. And we have a new workflow tool that can combine different codes together, like an ab initio code to get to Debye-Waller factors and various other codes. So like for doing RIXS, it would combine the XES, XAS, and the resonant denominator and just do them all at a press of a button. And finally, I'll acknowledge support largely from DOE Office of Science. This is Theoretical Condensed Matter Physics program, and then the Chemical Science program for the SPEC. And a whole bunch of people. Josh Cass is currently the lead developer, and Fernando Villa, and then lots of other people have helped all the way. This was a photo when we were all together for some reunion. And I'd like to thank you for your attention.
Thank you, Ron. Any more questions? Questions that were not asked during the talk? Yes,
I'm just curious about that self-energy. I mean, if I understand, you are using always Henry-Lundqvist, this Henry-Lundqvist potential, or the
GW.
imaginary or real part of this Henry-Lundqvist self-energy.
Yes.
I mean,
We use both real part and imaginary part.
yeah. So, is it also kind of a? Have you got the experience that it's really sort of universal, or?
Aha.
I can imagine that
The plasmon pole approximation is too strong in the near edge. Okay? What I mean is it's a single plasmon pole, so it overestimates the loss at the beginning. It's better to smear it out with real loss functions have a more systematic set of poles, and there's a particle hole continuum at the beginning. So their original plasmon pole makes a banana that has too much loss at low energies. So what we've found is it works great at high energies, a little bit too much loss at low. Now by too much, it's still a good banana. We find that as a great default. You can fix it up by putting in the real loss function, but it's not essential. And it's easy, then we just sum over a bunch of plasmon poles to get it. So it's a very fast calculation.
Other questions? Well, I've got two small questions, John. First, corpus, what is it? Is it any relation to the raven, or is it an
Yeah.
acronym?
It's a relation to the raven.
Okay.
Okay, so you know about ravens. They're intelligent birds. So my graduate student wanted to have an intelligent tool for combining codes together to produce a given property. So she called it Corvus, and somehow we don't have the Corvus logo there, but it's a very nice, beautiful black raven. Yes, that's the reason.
The other question is about your XPS spectra.
Yes.
Can we go
Yeah.
see? Yes, because usually when you try to reproduce theoretically satellites, you have missing features. But here it seems that you have an extra features. So
Yeah.
any idea what it could come from?
Well, this was an early calculation. This is 2015. It may be gone by now.
Okay.
But when you do a better job, you also get the surface states in here. Maybe this is a surface. I'm not sure. We should look at. We have more recent papers that that perhaps do a better job on this. So the way this is done, you calculate the density response to the suddenly turned on core hole in real time, and you get this oscillatory density fluctuations. And when you Fourier transform, you get a peak. And then the cumulant gives multiple peaks. Yeah, it's embarrassing. Okay, I will find the answer to that. That's
Okay, thanks, John.
it shouldn't be there, but
Other questions? Okay, so thanks again.
yeah, that was copper. Oh, sorry. I think that's.
No, before.
You know, our guinea pig is usually copper, but I should find that out. I can't really remember. I'll find out.
Just press the light.